Welcome back, ladies and gentlemen. We're going to be continuing our discussion around the physical properties of matter by looking into one of those properties, or, well, sort of three of those properties. Okay, one type of property, we'll go with that, specifically the state of matter. It's a property that you have been exploring since you've been like, elementary school? Yeah, you know what these are, even without me having to describe them. Gas, liquid, solid. And as a result of that, you, broadly speaking, know what's going to happen or what we're going to say, at least most of the stuff. But there's a few things here that you're going to be a little surprised about, I think. So let's start ourselves off. First, we've got the solid state of matter. Now, the solid state of matter is, the one with the definite shape and volume, right? So, for example, I can grab a solid object around me, like these scissors here, and there they are, scissors. They have a specific shape. They have a specific volume, right? As in, they have a shape, scissor shape, and they have a volume in the sense that they have a certain number of particles, and those number of particles take up a specific amount of space in the real world around us. Now, this tendency is unique to solids. Solids have both a definite shape and volume. The shape doesn't, as a result, depend on the container. That's why those scissors weren't spread out across the entire room like some kind of weird smear of plastic and metal. The particles are tightly packed together, often in an ordered arrangement. This one here is in a fairly important ordered arrangement called scissors. But they're definitely tightly packed together. That's why, they cut things. All right, I'm not going to cut this. I'll get in trouble. Solids will tend to expand slightly when you heat them. What that means, of course, is that as you sort of increase the available energy of the system, the particles start to spread out more. This is the reason why, for example, if you were dealing with a stuck jar lid and you're trying to get it off, one of the tricks is to put it under hot water, because what happens is that the metal of the lid will heat up and it will expand, meaning that it will have more room between the lid and the jar itself, because the jar is made of glass, and as we're going to see way later in the unit, maybe about 2 weeks from now, glass doesn't expand when it's heated, not nearly as much anyway. Usually, solids are incompressible. What that means is that if you try to take a solid at, say, room temperature, right? So if I tried to take those scissors again, right, and I tried to squeeze, to pinch these blades, to push them closer and closer together, it wouldn't do anything, because this is a solid and it's generally going to hold its shape. It'll change with temperature, but it won't change just by me squeezing on it. They got a range of densities, right? We've got here gold at 19.3, got iron at 7.87, we got the calcium at 1.54. Its range, the key thing is it's generally going to be above like about 1.5 up to 20, 30 even, or more. Next up, liquids. What do we know about liquids? Well, you know a lot about liquids. Their particles in liquid are close, but they're not in an orderly arrangement, right? Like if I had with me some kind of a cup filled with water, the particles are close. The water would be, as we see here, sitting on the bottom of the container. But even though they're close, it doesn't mean that they are sort of completely organized in really any way. The particles flow and move past each other in some random way. Because of this free flow, the liquids take the shape of their container, but some pour easier than others. Water pours pretty well, molasses or maple syrup, not so much. And of course, the key thing is that they don't fill the whole container. They just fill the bottom of the container. But whatever that shape is, they take that shape, right? If I poured water in this room that I'm in right now, it would cover the bottom of the floor, but it would take a square shape, because this room is, broadly speaking, square. The volume remains constant no matter what the shape is. This is why, for example, you can do this wonderful parlor trick. It'll delight all young children, where you take a very tall glass filled with water and you pour it into a very short glass. And yet they will tell you that the tall glass has more water in it, even though it's the same amount for both of them. And they will be mystified by this, because humans tend to think tall things just means there's more of them. It's just kind of how it works. But yeah, no matter what, if I take my glass of water and I pour it on the floor, the volume of water stays constant, right? I didn't get more water suddenly, which is really important because if we could get more water just by pouring it into something bigger, we wouldn't have nearly as much trouble getting a hold of water, if you know what I mean. Usually water is or liquids, sorry, are incompressible. Water itself is actually famously incompressible. Like water will not compress, which is actually pretty critical. If you guys have seen a lot of, fancy digging machines like a backloader or a bulldozer or any digging machine, you might notice that they've got these like cylinders on the side of the arms or the whatever. Those cylinders are filled with water. And it turns out that when you press on the water will propagate or carry that pressure all the way through to press on the other side. So you can imagine you've got this like cylinder of water, and when you press, the water doesn't like shrink down. When you press, it moves. And so that allows us to use water to basically dig into stone. Water is that incompressible. Now the in prefix there, in this case, in the case of English, it's a borrowed prefix from I think either Greek or Latin. Not sure which. Doesn't matter. Point is, incompressible means not compressible. They will expand when heated, just like all solids really, and all gases too, as we're going to see. And they can diffuse easily from areas of high concentration to areas of low concentration. Now, we've seen this, right? As we discussed in the other lecture, like diffusion is about the process by which particles will move through a material. So if I, for example, have pizza over in that corner of the room, the smell of the pizza will slowly slide through the air towards the other end of the room. This is caused by diffusion. You got some varying densities. Water, of course, is 1 gram per milliliter. Mercury is 13.53 grams per milliliter. Mercury is a strange one. Mercury is one of only two elements that are liquid at room temperature. The other one is bromine. And the net result of this is that mercury has so many strange properties as a result of its liquid nature. It's shiny and silver and yet a liquid. It was actually called quicksilver in a lot of different cultures and parts of the world, but because of this whole like silvery, moving, liquid type character, people generally assume that it must be magical or something. Mercury featured in a lot of medicines, which is a problem because the only people who could survive the incredibly important mercury elixirs were really rich and usually people in charge of stuff like kings and emperors. The reason this is bad is because mercury is a toxin. When you drink mercury, don't do it, please never drink mercury, it gets absorbed by your body and interferes with your nerves. So at first, the early onset of mercury poisoning causes you to get shakes because you can't control your nerve impulses anymore. So you start to get shakes and twitches. Then eventually it starts to affect your nervous system a little bit more acutely up in the head. You start to see things, you start to hear voices, you start to have other things like that, and then eventually you die. So it causes you to go quite literally mad. In point of fact, the phrase mad as a hatter came from England, where people who made hats, or haberdashers, ended up being surrounded by mercury all the time in order to make those big fancy top hats that everyone liked. And as a result of being exposed to mercury all the time, they all went nuts. The question is just how long. And if you were careful, it'd take a while. If you were less careful, you go crazy a lot sooner. All right, gases. There they are. Gases, of course, are very similar to liquids in some ways, right? They also freely flow around the container, and they will also take the shape of their container. The difference is they will take the shape of the entire container. A gas will expand to fill any space. That's why, for example, in this room here that I'm in right now, I don't have to worry about, going anywhere. I can just walk to any part of the room and there will be oxygen there for me to breathe in. It's not like the oxygen's all stuck in one corner somewhere because the gas expands to fill the space. This does also mean, of course, that, there it is, expand to fill any volume. The particles in the gas are much further apart than solids and liquids. And this, of course, means that they are very easy to compress. I can take gas and I can squish it down, which you've done if you've ever had, say, a Ziploc bag, right? You close a Ziploc bag, and inside the Ziploc bag you've trapped some air. And you can then squeeze the air out of the bag. All right, case in point, here we go. Got a bag. I'm going to seal it off. So in here right now is the air that I trapped in here, and I can compress the air to a point, right? Originally, the air was taking up quite a big space, right? But I can squeeze it down. I can make it take up less space, but eventually the pressure now is fighting back. And what will happen is if I try to push more, the bag is going to break in some place. I can also, of course, squeeze the air by opening up a section. If this particular bag was strong enough, I could keep compressing the air, making it take up less and less and less space. But as it is, that's the best I can do without breaking it, and I kind of need it, so I'm not going to do that. So it is easily compressed. It's the first one that is. It can also diffuse very easily from areas of high concentration to low, which is, again, very useful, because as anybody who's taken grade 10 science can tell you, or, well, hopefully anyone who knows people, we breathe in oxygen and we breathe out carbon dioxide. Well, I'm sitting here talking, which means I'm breathing. I'm breathing in oxygen like crazy, and I'm breathing out carbon dioxide. If the carbon dioxide didn't diffuse outward into the air to be replaced with fresh oxygen, I would run out of stuff to breathe because I'm staying in the same basic area to keep on frame. So in order for me to continue to live, I need this carbon dioxide that I'm breathing out to leave, to go away, to diffuse. And I need more oxygen to diffuse in. So this is pretty critical. You're going to get some pretty varied densities here. You got hydrogen, you got oxygen, you got chlorine. Chlorine, you'll see, of course, is pretty heavy. It's heavier than the oxygen. That means that chlorine will settle under oxygen. So like if there was chlorine in this room right now, right, I might have a band, I might have oxygen up here, but down by the floor, there would be chlorine, a chlorine gas. Now, chlorine gas is actually very dangerous. You don't want to breathe that in. That'll kill you pretty badly. It was actually used for a while as a chemical weapon, back in World War I, because chlorine is heavier than air, right? So it's heavier than oxygen. So when everyone's hiding out in little holes in the ground called foxholes, trying to make sure they didn't get shot with bullets, you'd release some chlorine gas and it would float in the breeze and it would sink into those holes. And now the people in there had a choice. Stay in there, breathe in chlorine. That's not going to go well. Get out of the hole, get shot by the people who released the chlorine. Also not going to go well. So, all right. Let's talk about something a little bit less ominous. Plasma. What is going on here? We just did the 3 states of matter, right? Well, sort of. As we've discussed, in the past, you guys covered the 3 states of matter. And maybe in middle school, you also covered the 4th state of matter. Plasma. Maybe. But if not, you're covering it now. Plasma is very similar to a gas in a lot of ways. So it's kind of a gaseous mixture of positive ions and electrons. What basically happens is that as you heat up or provide energy to a gas, eventually the gas has so much energy that it starts to like tear itself apart. Not the gas. Well, the gas, the particles start to tear themselves apart. The electrons get booted out and they're told to go find your own place. And in this case here, it talks about a temperature greater than 100 million Celsius. That's pretty crazy, right? It's not the only way to do it, but it's sort of one of the naturally occurring ways. As a result of this incredible temperature requirements, plasmas are very unstable. They require a ton of energy. Now, the energy could be in the form of heat, but it's not the only option. There are other options. This happens to be the most common form of matter in the universe, making up 99% of everything that we see. But it's the least common type of matter on Earth because of the incredible energy requirements. Anything that has this much energy would be incredibly dangerous, right? Like if plasma was on Earth just wandering around, we'd all be on fire. Now, plasmas do still exist on Earth, but they don't last very long. They will occur such as through, for example, lightning bolts. When a bolt of lightning strikes the ground, it creates a plasma for a brief instant, not because of temperature, although temperature is involved, but because of the energy involved, specifically an electrical energy, right? That's lightning, so it's electricity. So what we're dealing with here is that the energy involved in creating this lightning bolt, when it strikes, it creates a brief plasma. But the plasma, which remember is made of positive and negatives, once the energy level starts to drop because the energy gets sort of like, broadcast out in the form of light that we can see, these particles here come back together again because it turns out being in matter is a lot more relaxing than being in a plasma. So particles will tend to want to be in matter over a plasma. Other examples we see include stuff like the aurora borealis. Particles and energy come off the sun, right? That's what sunlight is, and they strike the upper atmosphere. And when they strike the upper atmosphere, they end up ionizing part of the atmosphere. They create a plasma. They create positive ions and negative electrons that all flow in the wind and in the magnetosphere, the magnetic field of the Earth, the thing that the compass points to. And this flowing light will create the aurora borealis. There's also one down on the South Pole, although we don't talk about that much because we don't live there. Anyway, stars, of course, and also fluorescent lights. Yeah, fluorescent lights, the lights that are currently off in this room, which we use to power most schools and other places, office buildings, they're actually also made of a plasma. It's just not a super hot plasma. The plasma is made into a plasma via electricity, just like the lightning. Because as we see here, right, a neon sign is a form of fluorescent sign. And we have a tube filled with, in this case, neon. The electricity is then turned on and it charges the gas. This creates a plasma inside the tube, and then that plasma will glow, releasing that energy back out. What color you get depends on what it was. Now, we call them neon signs because the first one we figured out was neon, and it made this nice orange. But every other color comes from a different type of gas. Right now we have mostly white lights coming out of the fluorescent lights. Those are a mix of argon and I don't remember what they are. There's like 2 or 3 gases that have to go together to make that white light. I'll have to look it up. Anyway, all of this basically is summarized on this slide here, right? And it's trying to talk about the fact that, right, as things add energy, you go from solid to liquid, liquid to gas, and then to plasma. And all of these things all require energy in order to work. Without energy, no luck. And that's the key. Each one of these states of matter is more and more chaotic, more and more disorganized. And in order to be disorganized, you need energy. If you add energy to a system, the system can expand. It can get a little more crazy, right? Like analogy time. If you're broke, you can't do much. But if I gave you all a bunch of money, not going to happen, but if I gave you all a bunch of money, you guys could go off and do all sorts of things. If you guys have no energy, you can't do much. But if you got lots of energy, you can do tons. So long as you got the energy. Once you spend it all, well, then you're out of luck. So everything about this is a measure of energy. As I add energy to the system, I gain more movement. I change from solid all the way up to plasma. So in some ways, it's actually kind of neat because, those ancient Greeks and other civilizations, they had this idea that there was earth, water, wind, and fire. And they're not totally wrong. It's just they thought those were individual, distinct, separate things when they're actually just distinct, separate states of the same thing. I could take liquid water and I can freeze it to make ice. I can boil it to make steam. I can take the steam and heat it up even further or give it energy in some other way in order to make a plasma. I could do it. Doesn't mean it's like easy. Plasma especially is a hard one to do. But it's interesting at how in some ways they were wrong and in other ways they were kind of right. So here we go. The angry particle trapped in the states of matter, trapped in a prison of oafs, awash in a morass of idiocy, adrift in a cloud of dolts, and lost in a chaotic sea of fools. You'll notice, of course, that here the whole space is filled because the solid is taking up all that space, but here the liquid, it's coming down, right? It's sloshing back and forth in the box. Here, it fills up the whole space. And here, we've got electrons as well as protons, or the rest of the atom that it stripped the electrons off of. All right, that's about it, ladies and gentlemen. Take a look at the next several pages. You guys have got a bunch of practice. You'll find the answers are either going to be located on the bottom of the page for each one of the practice question sheets or in my answer key in the drive. So take a look at that, and I will see you guys next time.